Dieckmann condensation. Dieckmann condensation is basically an intramolecular Claisen ester condensation. Let's say that you have two ester functional groups present in the same molecule. Then that compound can undergo Dieckmann condensation provided it has the ability to form the 5-membered or 6-membered ring structure. Here are some examples for Dieckmann condensation. This compound right here is a 1,6-diester. Why it is a 1,6-diester? Because if you're going to consider this carbon as carbon number 1, okay, 2, 3, 4, 5, 6. The second carbonyl group is at position 6 with respect to the first carbonyl group, right? And you can see that there are two ester functional groups, and therefore this is called as 1,6-diester. When 1,6-diester reacts with a base, it's definitely going to undergo intramolecular Claisen ester condensation to give us this cyclic structure, beta keto ester. So here is a beta keto ester, and you can see a 5-membered ring structure is formed in between. This one right here is 1,7-diester. Here again, it will be beta keto ester because the product that you get in a normal Claisen ester condensation is beta keto ester. Right? But here, since the two functional groups are present in the same molecule, it's going to result in the cyclic structure. Dieckmann condensation will only be possible if it's going to lead to the 5-membered or a 6-membered ring structure. Let's take a look into the mechanism to find out how a 5-membered or a 6-membered ring is formed in Dieckmann condensation. This molecule right here is a diester. To be more specifically, it is a 1, 2, 3, 4, 5, 6, 1,6 diester. Now the first step here is the base is going to abstract the alpha hydrogen. So here in this molecule, we have two alpha hydrogens. So this is an alpha carbon, this is also an alpha carbon. But both of these alpha carbons are equivalent because there is some sort of symmetry in this molecule, because of which it's going to lead to only one product. In some cases, there might be two different enolates that will be created, but whichever forms the most stable structure, most stable cyclic compound, that will be the major product. But here in this case, we are only forming one type of enolate ion, where this base is going to go grab one of these hydrogens, right? And it's going to create as the enolate ion. Okay, let's draw the structure for the enolate ion. So here is the enolate ion. And once this enolate ion is formed, this is going to make a nucleophilic attack on the carbonyl carbon of the other ester functional group and thrust these electrons onto oxygen. Now let's identify how many carbons are going to be involved as it forms this cyclic structure. 1, 2, 3, 4, 5. There are 5 carbons that are involved, and therefore this is going to form a 5-membered ring structure. So here is the new carbon-carbon single bond that has been formed. We can find it here. This carbon right here should have the oxygen, right? Singly bonded oxygen with its electrons on it. And it should also have the methoxy group on it. So here is the methoxy group. And here is the new carbon-carbon bond that is formed between the alpha carbon and the carbonyl carbon. Okay. And on this carbon, we do have the ester functional group. So let's also draw the ester functional group. Now after this, the pi bond will be reformed where these electrons will come in, and because there is a leaving group, this is going to leave. And this is going to result in beta keto ester. So this is a beta keto ester.